There are many forms of geometry. The most commonly taught form is geometry on a plane. Geometry on a plane is called Euclidean geometry. This form of geometry is also taught in schools.
Euclidean geometry is completely based off of 5 postulates that were stated by a Greek mathematician named Euclid.
Euclid's first postulate states a straight line segment can be drawn by joining any 2 points. Euclid's second postulate states any straight line segment can be extended indefinitely in a straight line. The third postulate says, given any straight line segment, a circle can be drawn having the segment as radius and one endpoint as center. His fourth postulate states, all right angles are congruent. And finally, the fifth postulate says, if 2 lines are drawn which intersect a third in such a way that the sum of the inner angles on one side is less than 2 right angles, then the 2 lines inevitably must intersect each other on that side if extended far enough. The first 4 postulates could be proven, however, the fifth could not.
In 1817, Johann Gauss secretly began working on another form of geometry where a point has multiple lines through it that are also parallel to another line not containing that point. Hyperbolic geometry was formed when mathematicians changed the fifth postulate of Euclidean geometry. In hyperbolic geometry, the fifth postulate states, given a line L and a point P not on L, there are infinitely many lines that pass through P and never meet L. Hyperbolic geometry was independently discovered by a Russian named Nikolai Lobachevsky in 1829 and a Hungarian named János Bolyai in 1831. Although these two discovered it, they could not come up with a legitimate model to prove it true. Several years later, a man named Eugenio Beltrami created a model that proved hyperbolic geometry to be just as true as Euclidean geometry. One of the main models of hyperbolic geometry is called the Poincare disk model, which was named after the mathematician Henri Poincare. The Poincare disk model is a stereographic projection of a hyperboloid. A hyperboloid is the rotated 3D representation of a hyperbola. The stereographic projection of this is basically the bird's eye view of one piece of the hyperboloid where you are viewing from the closed end. The Poincare disk is a two-dimensional representation of hyperbolic space. To give you a deeper understanding of the model, figures closer to the middle will appear bigger than those farther away. All of the stick figures are the same size, yet the ones toward the boundary of the disk look smaller because of the distortion of hyperbolic space. The boundary of the model is dotted to show that it is infinitely expanding. On the Poincare disk model, all straight lines appear as orthogonal arcs to us. The term orthogonal means they are perpendicular to the boundary of the circle. The lines appear as arcs to us because our eyes' inability to perceive hyperbolic space with our limited Euclidean perspective. Say this arc represents our line L, and here is our point P. Through P, we can draw as many orthogonal arcs as we want. As long as those arcs don't visibly intersect L, they are parallel to L. You might be thinking there is no point of this because arcs are not straight lines, which the fifth postulate talks about, but they are. Although they looked curved to us, to a hyperbolic being living on the hyperbolic plane, these curves would appear as straight lines, and all the lines would be going through P and never touching L. Therefore, the lines through P are parallel to L, proving the fifth postulate of hyperbolic geometry is true. Another way we can model hyperbolic space is imagining the shape of a saddle. This is not as easy visually as the Poincare disk model, but this model will prove the fifth postulate to be true as well. Hyperbolic triangles can be created from the intersection of 3 orthogonal arcs in hyperbolic geometry, just as triangles can be made by lines in Euclidean geometry. Each of the 3 angles in a hyperbolic triangle is less than its Euclidean counterpart. Since the lines are now arcs that bend inwards, the lines making the vertices of the hyperbolic triangle are closer together, which makes them more acute. If each hyperbolic angle is more acute than its Euclidean counterpart, we can determine that the sum of the angles in a hyperbolic triangle is less than 180 degrees or pi radians. We can also find the area of hyperbolic triangles. The area is pi minus the sum of the three angles, all multiplied by r squared. In the formula, r equals 1 over the square root of negative k. The variable k is the constant of Gaussian curvature. In almost every situation, k equals -1 for hyperbolic space. Knowing this, we can simplify the area of a hyperbolic triangle to be pi minus the sum of the three angles. Using the area formula of hyperbolic triangles, we can deduce that all hyperbolic triangles with equal angle sums have equal areas. Ideal triangles are a special kind of hyperbolic triangle whose vertices lie on the boundary of the Poincare disk. Since these vertices lie on the boundary of infinity, the lines get infinitely closer together, making each angle 0 degrees or 0 radians. If every angle is 0, that means the area of ideal triangles is pi units, while the perimeter is infinite due to the vertices stretching on forever. Technically speaking, ideal triangles are not real triangles, but the theoretical idea of them is used to prove the formula for the area of hyperbolic triangles to be true.
Elliptic geometry uses the first four postulates of Euclidean geometry. However, the fifth postulate states, if L is any line and P is any point not on L, then there are no lines through P that are parallel to L. Elliptic geometry is on a curved sphere instead of a flat plane. Great circles, or the largest circles on spheres, serve the same purpose in elliptic geometry as lines do in Euclidean geometry. This is because in elliptic geometry, the great circle is the shortest distance between 2 points. These great circles have a finite length, however, they never end. Elliptic geometry was first studied by George Riemann. To prove the fifth postulate in elliptic geometry, we must begin by assuming the great circle made between points A and B, and the great circle made between points A and C are longitude. Then we must assume the great circle made between points B and C is latitude. In Euclidean geometry, line AB is perpendicular to line BC, and line AC is perpendicular to line BC. Therefore, line AB would be parallel to line AC. However, in elliptic geometry, circle AB will intersect circle AC at 2 points, so they are not parallel. On a sphere, the sum of the angles of a triangle is greater than 180 degrees. To prove this, we must assume the same longitude and latitude lines as we did before. Then, we know that angle ABC equals 90 degrees and angle ACB equals 90 degrees because longitude and latitude lines are perpendicular to each other. Then, looking at the diagram, we can see that angle BAC does not equal 0 degrees. Therefore, the sum of the angles in triangle ABC is greater than 180 degrees. Girard's theorem was found by Albert Girard. It is used to find the area of a triangle with angles alpha, beta, and gamma. Girard's theorem states the area of a triangle with angles alpha, beta, and gamma on a sphere with radius r can be found using the formula area equals r squared times alpha plus beta plus gamma minus pi. Points in elliptical geometry are absolute poles to an absolute polar line. This means that a point has a corresponding absolute polar plane where the point is perpendicular to every single point on that plane. This also means that a line has a corresponding absolute polar line where the line is perpendicular to every point on the absolute polar line.